For the next corrective measures, we shall be looking at callbacks and checkpoints. Callbacks simply are tools we use during training or testing in order to carry out certain specific tasks. Now, you may have noticed that so far we've been using callbacks, especially when we're printing out the lost values per epoch or after a given batch. Defining a callback in TensorFlow is made very easy. All you need to do is to define this class and then make it inherit from TensorFlow's callbacks.callback class. Then you specify these different methods right here. Now these methods are defined by TensorFlow, and in this example we've worked with only 2 of those methods. The first one being onTrain batch n. So this means when training after a given batch, we're gonna output this. As you could see here with the default callback right here, we receive this outputs or this lost values and the metrics after the epoch. But here we're wanting to print all these values after every batch. Now we also have this onEpochN method right here. This method, as you could see, takes in the epoch, and then we have this logs, the same as what we had here. Now the logs here basically contain the values for the loss and then the metrics. And so as you could see, with this we have the batch, and then with this we have the epoch. In the documentation, you could see all those different methods. We have on batch begin, so anytime the batch wants start processing a given batch, we could take a certain action like printing out certain values. On batch end, this is what we've seen already. That's after the batch is after processing a given batch, we could output certain values. We have on epoch begin, that's before starting with an epoch. Here we have on epoch end, at the end of an epoch. On predict batch begin, this is when doing model prediction. So this, as you could see, is for training, but when doing model prediction, you see they specify on predict batch begin, which is different from the on batch begin, which is for training. So as we said, this is for prediction, this for prediction. This for testing, on train batch begin, on train batch end, on train begin, on train end, set model, set parameters. So basically here are those methods which we could call very easily and then take certain actions. Like for example, after each epoch we could save the model loss and metrics in a file, like a text file. And as we've seen right here, that is very easy. If you have to save these parameters in the text file, all you need to do is to create a text file and then get this logs and then simply save the text file in this onEpochN method. Now that said, we just come in this compile and we have the callback. So callbacks actually takes this, and then we'll define this lost callback right here. Just like with the metrics, you have a list, so that's it. Put this comma and we're fine. So that's how we include callbacks in our training process. Now that was more of a general way of looking at callbacks. Let's look at some more specific callbacks like the learning rate scheduler. Before continuing with that, let's do a slight modification. This is not meant to be here. It's actually in the fit here. So we take this and then we have that. So here we have our callbacks such that while training, we could print out these values and also print out those values. The next callback which I'll be looking at is that of learning rate scheduling. Suppose we define a learning rate scheduling strategy such that for the first 5 epochs, or let's say the first 4 epochs, the learning rate is initially, we could say 0.1, or let's say 1 times 10 to the negative 3. Let's suppose 1 times 10 to the negative 3, or even say 5. And then from the 5th to the 9th epoch, the learning rate goes to 1 times 10 to the negative 4. And then from the 10th epoch onwards, the learning rate b equals the current learning rate times 1 times 10 to the negative 2. Again, TensorFlow makes this quite easy to do. All you need to do is define this learning rate scheduler function right here, which takes in the epoch and the learning rate. So for epochs less than 5, we have the learning rate to be this learning rate initialized to 1 times 10 to the negative 5 LR init. And then for epochs greater than or equal 5 up to 9, the learning rate is multiplied by actually 10. So we have the answer to be equals 1 times 10 to the negative 4. So that's it. And then from here onwards, our learning rate is multiplied by 0.01, which is 1 times 10 to the negative 2. Once we define this, our learning rate scheduler function, we now have this learning rate scheduler callback, which comes with TensorFlow, which we now just simply pass in this function. So we just pass in this function name in here, and the job is done. So we call this our learning rate scheduler. Then we just simply add this to the callbacks, our scheduler, and that's okay. So we'll run this, run that, and we're fine. Many times when doing training, we get to a point where the loss or some metric value plateaus. That is, we don't get maybe any reduction in the loss as we keep training for a fixed learning rate. Now, what we could do is to automate this process of reducing the learning rate so that the model could converge further. We could use TensorFlow's reduce learning rate on plateau callback. Again, TensorFlow makes it very easy to create this callback. So right here we have our reduce learning rate on plateau callback. With the monitor, we specify the exact parameter we shall be monitoring. This could be the accuracy, it could be the validation loss, or whatever metric or loss value we're trying to monitor. Now, this monitoring is done such that if after 3 epochs the loss value doesn't drop, then the current learning rate is going to be multiplied by 0.5. So this means if our learning rate is say 0.001, then if after 3 epochs the loss doesn't reduce, we have 0.001 times 0.5, and we get to 0.0005. So now that becomes our new learning rate if after 3 epochs the loss doesn't drop. And also this minimum learning rate is specified so that there is a threshold below which our learning rate can't go. So in this example, if we start with this learning rate and we drop in like this, we could specify a threshold of 0. like that. So we have this learning rate, or this minimum learning rate, below which we wouldn't keep dropping this learning rate even if the loss value doesn't drop. Also, by default, there is a mode which is auto. You could choose between automatic, you could choose between mean, and you could choose also max. Now, by default, it's automatic, meaning that the callback automatically knows that for a loss we are trying to reduce its value, so it sees this auto like a mean. Whereas if we had an accuracy here, we'll be having a max. So we'll be having a max value for which after 3 epochs, if the accuracy doesn't go above that value, then we would have to reduce the learning rate. So let's take this off, and that's fine. So with this, we have our learning rate plateau, which we just simply add to our callbacks. Yeah, we have learning rate plateau, and that's it. Take this off, and then we run. The next callback which I'll be looking at is that of L is stopping. Now, if we go back to this model we had trained previously, we would see that this is something which is very typical to see when training models. Yeah, as you could see, the validation loss drops initially, gets to a point where it starts to increase while the training loss keeps dropping. This is clearly an overfitted model. And so what we could do is we could design a callback which monitors this validation and training loss, such that after a certain number of epochs, if the validation loss keeps increasing while the training loss keeps reducing, then we could simply stop training. So because it's actually needless training from this point, because the model is no longer learning from the data, as it can't even generalize to the validation data set. And so when this kind of model is going to be fed with some new data which it has never seen, it obviously is going to give very poor results. And so that's why it's very important to stop the training once the model starts overfitting. Notice how the L is stopping callback has a similar pattern with this callback and this other callback. Here again we have the L is stopping. We're monitoring the validation loss. This is more common than monitoring the loss, because many times we want to be sure that the validation loss hasn't started increasing, or it's just maybe stagnant. So in this case, we monitor the validation loss. We could take a patience of say 5. So after 5 epochs, if the validation loss keeps or stays the same or starts increasing, or doesn't go below the lowest value it has had since training began, then we would have to stop training. The mode here is auto. It could be min or it could be max, but for the validation loss we could either put it to be auto or min. Same as we could have the validation accuracy. So instead of that, we could put this validation accuracy and then we'll set it to max. So let's put it back, validation loss, and then auto, patience 5. Okay, now we run this again, and similar to what we've been seeing, we just have the ES, and that's fine. The other callback which I'll be looking at is this checkpoints. Suppose you're training your model, as we've seen here, you've trained for those 15 epochs, and then maybe you forget to save the model, or something goes wrong, and then maybe your PC or whatever machine you're using goes off. This kind of situation may be very frustrating, as you would have to retrain again your model in order to get back to its previous state. Now, in order to solve this problem, what we could do is, as we're training, we could monitor the loss values or some metric value such that the model is automatically saved, or more precisely, the model weights are automatically saved, such that the next time you come to do training or prediction or whatever you want to do with the model, you just have to load the model from a given point. Now that said, we have this. We could specify the checkpoint file path. So yeah, we have the ImageNet 200 and some mobile net based. We given it this the extension we're using for the weights. It could be HDF5 or simply H5. So there we go. We have the checkpoint file path. We run that, and then we have the checkpoint, which is defined as such. First, we have the model checkpoint callback. The file path takes in this. we save the weights only. So basically we're just saving the weights, not the weights and the model. Then after saving the weights, or after specifying that we save only the weights, what we're monitoring is the validation loss. Now what we're saying here is, if the validation loss drops, we save the weights. So if the validation loss drops and we had a previous weight which has been saved, that previous weight is going to be removed or replaced by the new weight when the validation loss, or the new weights for which the validation loss has a lower value. Then we just simply keep on training, and at the end we end up with the weights for which we have the lowest validation loss. We could change this to simply the loss or accuracy or some other metrics, and then if it's accuracy, yeah, you have the max. So let's take this back, and we have the validation loss. There we go. And then also we save the best only, so we specify that we're saving the best only, and that's it. So once we have this, we run it, and then we include again in our callbacks the checkpoint. So apart from the fact that it helps us save our model weights in case something unexpected may occur, we also save the best model weights. Our next corrective measure will be learning how to use the tensor bar callback to track